Good afternoon. My name is Michael Singh, and today I will be discussing the biomechanical evaluation of a novel equine hock arthrodesis technique. Distal hock osteoarthritis is a common source of poor performance in all horses, with hind limb lameness persisting in 25 to 50% of medically managed cases. And the low long-term success rate of current non-surgical and surgical methods means that veterinarians often perform arthrodesis and facilitated ankylosis as a way to treat the disease. Um, However, no one method has been proven to be successful over the other, and um, approximately 59% of equine hocks that are treated with traditional arthrodesis are successful, with 41% of them being unsuccessful. So there's an approximate 50-50 chance of improved condition following the traditional method. Therefore, we propose a novel arthrodesis technique that employs trans-articular screw placement to provide compression across the joint surface. And due to the limited biomechanical data that has been performed on current arthrodesis methods in the tarsal joints, we have an opportunity to develop a clinically superior arthrodesis method with improved joint fusion. To this end, we performed the present study, which assesses the biomechanical integrity of horse hocks treated with the novel arthrodesis technique. And we compared the loading of the horse hocks in torsional and compression regimes against control tarsi, and performed a pilot study to evaluate the fixtures and validate them, as well as the methodology for potting and testing a healthy hock. We developed an 80-20 fixture constructed with a dual column design, and we also manufacture steel pots to pot the hock samples using 50-pound Labstone. The 80-20 fixture was constructed with two vertically opposed yokes that were centered to ensure that the hock was centered during potting, and a horizontal bar to ensure that the given pot that was being potted was leveled and that there was a uniform hold between the Labstone and the hock. We also incorporated a sidearm with a hook to center the lower end of the hock during potting. And we also incorporated a dual column design in the 80-20 fixture so that we could ensure adjustable distance between the yokes and therefore account for different sizes of the hocks. The testing procedure for the equine hock potting started with thawing for about 24 hours at 4 degrees Celsius in the freezer of the equine hock sample. The equine hock sample was then dissected at the bone ends, the tibial and the femoral end, and the tibial end was drilled with a through hole was drilled to the tibial end with a diameter of 1/4 inch, and it was then mounted on the 80-20 fixture. It was then potted using the 50-pound Labstone, and after 30 minutes of curing, it was flipped, and a second potting was done following the same procedure on the femoral end. The equine hock was then mounted on an Instron dual column universal testing system, model 5984, and it was mounted to perform the axial compression with dorsoplantar bending using a load frame of 150 kilonewtons and a ramp rate of 0.25 inches per second. And this equine hock was compressed until failure was achieved. We then constructed a load displacement curve of the actual compression test, and we determined that the maximum load experienced by the equine hock occurred at 472.73 pounds at 0.162 inches. We also noted that there was a massive decrease in load experienced by the hock as it was compressed, and the high total displacement was observed for the machine despite the low relative displacement of the hock. The low loading of the healthy joint can be attributable to the low resistance of the joint, which is caused naturally by the lack of fusion, which was expected. However, the patellar tendon was severed during the dissecting, which was unintentional, but also reduced the resistance of the joint. And the 2D rotational freedom of the steel pots during compression also meant that the resistance of the joint was lowered. Lastly, we noted that there was insufficient distance between the bone ends, which first caused, it was a factor in severing the patellar tendon. And it also ensured that the femoral end wasn't seated properly into the Labstone for testing. Future work for this project will include taking into account axial compression tests on traditional and novel arthrodesis hock samples, as these are expected to have higher resistance due to the fusion from the arthrodesis. And we will also determine if one of the pods should be fixed completely during the testing in order to have a better one-to-one relationship between the linear displacement of the testing machine and the angular displacement of the hock. We will also acquire longer hock samples to prevent the errors with the dissection and also to ensure that the podding is stronger in the future when we perform the tests. And lastly, we will perform torsional loading tests on healthy and torsional loading tests on healthy and arthrodesis hock samples. These are my references, and I would like to thank the BMEL laboratory and the LabE laboratory for providing us the equine hock samples. Thank you.